So when we started solving yesterday, some of the problems were super easy. Like all you would do was type in like natural log 12 into your calculator, turn it into a decimal, and then like solve for x. Some of them were a little bit harder because the x was in the log. So when the x is in the log, there's a process of getting it out. You have to like rewrite it as an exponential equation. That process is still going to happen today, but it's going to be like the last steps of the problem. What we're going to see today is that there may be more than one log in the equation, and you actually have to use the condensing properties that we just quizzed on today. You actually have to use those condensing properties to sort of smoosh all your logs into one log so that you can then solve it easier. So you kind of start to see the relevance of these properties today. Now, before we get into actually doing it, there's an important aspect of these problems that we have to talk about. And that is the idea of the domain. So I want you to think back to when we first learned like what was a logarithm. We talked about the fact that you can't have like, let's see here, you can't have a 0 in that position, right? It doesn't make any sense. What else can you not have in that position? A negative number. So now when we are solving for an unknown number, so x is holding the place for some mystery number, we actually have to keep in mind that there might be some values of x that are not allowed. And when we go about using solving tools and properties, sometimes we do all of our math right and we get what's called extraneous solutions. We get extra answers that don't make sense in the context of the problem. And so you do need to watch out for that. So let's start by looking at something like this. Think about what would happen, right? X is holding the place for a mystery number. What if I got an x value of -2? So let's think about what this would look like. This would look like y equals log of -5, right? -2 minus 3. Would that be okay? No, that wouldn't be okay. So that is in the restricted domain, right? That is not an allowable answer for x. So the easiest way for you to think about what's allowed and what's not allowed is to think about always keeping this positive. Right? Always keep it positive. It's kind of like a good life lesson or thought of the day, if you will. All right? So we're going to keep this positive. We also need to keep it real. All right? And that kind of comes into play over on the second one. So if I was going to keep this positive, what would I have to say about x? X would have to be greater than 3. Exactly. So as long as you give some thought to that before you go about solving it, when you solve this problem, if you get like x equals 7, then you're fine. But if you go about solving this problem and you get x equals 7 or x equals -1, the 7 might work just fine. It's an allowable answer, but the -1 would be extraneous. Okay, so you just always want to check those. This one's a little bit harder because it's got this whole like x in the numerator and x in the denominator. So we kind of have to consider all the placements of x. So if we just were to consider this one, we definitely want to keep it positive. If we come down here, we definitely want to keep it positive. So if I'm going to keep that positive, x needs to be bigger than 5. But I also have to keep it real. So what I mean by keeping it real is don't do something like divide by 0. Or don't do something like square root a negative number. So in this case, I also have to make sure that x never becomes a 5. All right, that would, that allows me to keep it real. So if I actually had to state the domain for this, which isn't a part of these problems, but if I had to state the domain for this, it might be easier if we like plotted it on a number line. So there's this restriction that goes like that. There's this restriction that goes like that. Which one of those is more restrictive? The 0, the blue one. So the blue one would be the overall thing. We just need to make sure we always keep it greater than 0. All right, so as long as you give some thought to that at the beginning of the problem, you're gonna be fine. So when we solve these, you do need to watch out for those extraneous solutions. Don't allow any x values that would result in a 0 or a negative number inside of the log. And then I would say always plug your solutions back in. But honestly, if you take the time up front to think about, okay, I need to make sure that all of my allowable answers are bigger than 5, then you're probably going to catch the extraneous ones. You know, the concept of plugging it back in is to check for extraneous, but if you think about it in advance, then maybe you don't have to do the plugging in step. So let's try one. One of the things that you'll see in today's problems is that there will be multiple logs. In yesterday's problems, there was usually only one log. So the first step that we have to do is kind of get all the logs on one side and just the numbers on the other side. And so I would go ahead and just add this over. So then we've got, you know, a log 3 plus a log x equals a 2. And once you get all the logs on the same side, now we're going to use our condensing properties to pull them together into a single log with one argument. So for this particular one, this would turn into log of 3x equals 2. Then, once you have the single log, if your variable is in the log, which it will be in all these problems, your variable will be in the log. Now what we need to do is go ahead and rewrite it in its other form to get the x out of the log. So, right, there's this piece, and there's this piece. And so if I rewrite that, that would be 10 squared equals 3x. And then that's just an algebra equation where I can solve for x. So I've got what, 100 equals 3x. So x is 100 divided by 3. Now let's definitely go back and just double check and make sure that that does not break any of my rules. When I come back up here, because of this, I need to have x greater than 0 because I got to keep it positive. My x value is greater than 0, so I'm good. So that's your process for today. Yeah?
Where did you get the 10? Or like, do you just like apply it?
Well, remember that any log that doesn't have a base number written is automatically base 10. So this problem started off as a base 10 problem. And so when I condensed it down to a single log and I needed to rewrite it, I just put the 10 in there as a reminder, okay, I'm going to have a base 10 to the power of 2 equals 3x. Yeah?
Do you have to switch the, like, the 3 over, like, put it 3 over 100 because you did, like, an inverse?
Like, this, rewriting it in its other form is a little bit different than creating an inverse. When we create an inverse, we would switch our variables, and that's where the opposite operations come in. Here we didn't do a switch of the variables. Does that make sense? Okay. All right, so let's try another one. So this one has 3 logs in it. We've got a log x. So I'm looking at this and I'm going, okay, I better keep x positive. I've got a log base 2 of 3, and then I've got a log base 2 of 16. Now this, that's like probably some messy decimal. I don't want to deal with that. But what about this? Can I simplify that? Okay, so look for that. If there's, I mean, they might be in the middle of a problem somewhere. Simplify that. Isn't that just a 4? Okay, so 2 log base 2 of x minus log base 2 of 3. I'm not going to do anything about this one. I'm going to condense it. Equals a 4. So now I'm going to go ahead and condense these 2 logs. This 2 will come up and be an exponent on the x. So I'm going to get an x squared, and it's going to be, ooh, wait a second. The minus means it's going to be divided, so I'm going to have an x squared divided by 3 when I condense that. And then that equals a 4. So at this point, I've got a single log. I've got my 3 parts. I got this part, I got this part, and I got this part. So I can just rewrite it in its other form so that I can get the x out of the log. So this would be 2 to the power of 4 equals x squared divided by 3. And now it's just an algebra problem. So 16 is equal to x squared divided by 3. Let's see. If I magnify both sides times 3, I would get 48 is equal to x squared. And we can go ahead and square root. Now what comes with the square root? Ah, good, Hugo. Plus or minus. Don't forget that. So we've got x is equal to positive or negative, and I can also reduce this, what, like 16 times 3, so 4 square root 3. But didn't we say in the beginning that x had to be greater than 0? So this part of it, this version of it will be extraneous. Right? Because if we look back at the original problem right here, from the very beginning we said, oh, okay, we have to make sure that x is always greater than 0. So that one is extraneous, and my only solution is positive 4 square root 3. So that's what I mean by extraneous solutions will present themselves often because of just some of the mathematical processes that you end up doing. All right, so this one has only 2 logs. They're on different sides though, so let's put them on the same side, condense them together. And in order to do that, I would subtract this log over. So that's going to look like this. Log base 3 of x plus 8 minus log base 3 of x equals 2. So now I would come and condense these into a single log. Because of the minus, I'm going to have the arguments divided. So this will be log base 3 of x plus 8 divided by x equals a 2. Now I am ready to rewrite this. Here's my 3 pieces. That's the only way to get the x out of the log is to rewrite it. So this would be 3 squared is equal to x plus 8 over x. And now I just have an algebra problem that I'm solving. So this is 9 equals x plus 8 over x. Maybe just slap this over a 1. Do your cross products. 9x equals x plus 8. Subtract your x. 8x equals 8. So x equals 1. And then I'll look back and just double check. Okay, if I plug in a 1 here, that keeps it positive and keeps it real. If I plug in a 1 here, keeps it positive, keeps it real. So we're good on that. All right, so this last one maybe has a little bit harder. You know, I want to expose you to some other little quirks about it. 2 logs, get them on the same side, get the 2 over to the other side. It looks harmless right now. And add the 2 this way. All right, so we've got log base 2 x minus 3 plus log base 2 of x equals 2. So here's where I have to be careful. When I go to condense these, what's going to happen, because they were added, what's going to happen when I condense them? They're going to be multiplied. But this has 2 things, and they both have to get multiplied. Andi?
After you distribute it, can you condense it again?
Not necessarily. Because once you condense it, you only have 1 log. So it doesn't really matter how many terms are in that log. You've already condensed it into 1 log. So when we condense this into 1 log, careful, it's going to be an x multiplied by an x minus 3. So you kind of have to do the distributive property in there. And when you do that, you're going to get a quadratic. You're going to get x squared minus 3x. So now when I go to do my rewrite, and I've got this piece, I've got this piece, I've got this piece. When I rewrite it, 2 squared equals x squared minus 3x. How do we solve a quadratic? Either the quadratic formula or hopefully it factors. Okay, so we have to set it equal to 0. All right, this would be, why don't I just subtract this 4 over this way? So then this looks like 0 equals x squared minus 3x minus 4. And now, I think this does factor. Okay, x minus 4, x plus 1. So I've got 2 answers, 2 potential answers. X could be 4, or x could be -1. Sometimes they will both work. Sometimes neither of them will work. Sometimes one works and one doesn't. All right, so we're just going to check it back in the original. If I plug in the 4, that's positive and that's positive. So this one checked out here and here. If I plug in the -1, it fails right here. It also fails here. It only has to fail in one spot. Okay, so this one is extraneous, and your only answer is 4. So there you go. That's some log solving for you.